Tonight, we're going to witness one of the most violent encounters the universe can produce. Imagine two dead stars, remnants of lives already lived and ended, falling toward each other across millions of years. One is roughly the size of Earth, a white dwarf, the dense core left behind when a star like our sun dies. The other is barely the size of a city, a neutron star, so dense that a single teaspoon of its material weighs more than a mountain. And here's the part that should stop you in your tracks. The smaller object, the one you could drive across in minutes, is about to tear the larger one apart, not by crashing into it, by pulling it to pieces with gravity alone. And what happens next is unlike anything else in the universe. Before we dive in, if you find these kinds of deep explorations of the cosmos fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with the two objects at the heart of this story, because before we can understand what happens when a white dwarf meets a neutron star, we need to understand what each one actually is. And the truth is, both of them are among the strangest objects the universe has ever produced. They're both stellar corpses, remnants left behind when stars die. But they're very different kinds of corpses. One is roughly the size of a planet, the other is smaller than a city. One is made of tightly packed atoms, crushed together until their electrons resist any further compression. The other is made of matter so dense that atoms themselves have been destroyed, their protons and electrons squeezed together into a sea of neutrons. And somehow, despite these enormous differences, the universe occasionally brings these two objects together. When it does, the result is one of the most extreme physical events we can imagine. But to appreciate just how extreme it is, we first need to understand what makes each of these remnants so remarkable on its own. Let's begin with the white dwarf. Every star you see in the night sky is burning fuel. Deep in each star's core, nuclear fusion converts lighter elements into heavier ones, releasing enormous energy. This energy pushes outward, balancing the inward crush of gravity. As long as the star has fuel to burn, this balance holds. The star stays stable, shining steadily for millions or billions of years. But fuel doesn't last forever. Our sun has been burning hydrogen for about 4.5 billion years, and it has roughly another 5 billion years of hydrogen left. After that, things change. When the core runs out of hydrogen, it starts fusing helium into heavier elements like carbon and oxygen. The outer layers of the star swell enormously, turning it into a red giant, a bloated shell hundreds of times wider than the original star. For a star like our sun, this is essentially the beginning of the end. The red giant phase doesn't last long in cosmic terms. Over the course of a few 100 million years, the star's outer layers drift away into space, forming a beautiful expanding shell of gas called a planetary nebula. What's left behind is the core, a dense, incredibly hot ball of carbon and oxygen about the size of Earth. That core is a white dwarf. Now think about that for a moment. The sun is about 864,000 miles across. It's enormous. You could fit about 1.3 million Earths inside it. But when the sun dies, all the mass that doesn't get blown away in that planetary nebula gets compressed down into something roughly 7,000 miles across. That's about the diameter of Earth. So you've taken a significant fraction of an entire star's mass and packed it into a volume no bigger than a planet. The result is extraordinarily dense. A typical white dwarf contains about half the mass of the sun, sometimes more, crammed into a sphere about the size of Earth. A teaspoon of white dwarf material would weigh about 5.5 tons. Not pounds, tons. That's roughly the weight of an elephant packed into a space you could balance on the tip of your finger. What holds a white dwarf up against gravity? It's not fusion. A white dwarf has no fuel left to burn. Instead, it's held up by something called electron degeneracy pressure. This is a quantum mechanical effect. When you compress matter to extreme densities, the electrons in the material resist being squeezed any further. They push back, not because of any force between them in the traditional sense, but because of a fundamental principle of quantum mechanics that says no two electrons can occupy the same quantum state in the same place at the same time. This resistance, this quantum pressure, is what prevents the white dwarf from collapsing further. It's an incredibly stable configuration. A white dwarf can sit in this state for trillions of years, slowly cooling and dimming as it radiates away its remaining heat. But there's a limit to how much mass electron degeneracy pressure can support. In the 1930s, a brilliant Indian astrophysicist named Subramanian Chandrasekhar calculated that if a white dwarf exceeds roughly 1.4 times the mass of the Sun, electron degeneracy pressure simply isn't strong enough to hold it up. Above this threshold, known as the Chandrasekhar limit, the white dwarf would collapse under its own gravity. This discovery was revolutionary. It told us that white dwarfs have a maximum mass. They can't just keep getting heavier and heavier. There's a ceiling, and beyond that ceiling, something dramatic has to happen. Most white dwarfs sit comfortably below this limit. Typical masses range from about half to just over 1 solar mass. They're made mostly of carbon and oxygen, the elements their parent stars were fusing in their final stages. Some lighter white dwarfs are made primarily of helium, and some of the heavier ones contain significant amounts of neon and magnesium. But carbon and oxygen white dwarfs are the most common, and they're the ones most relevant to our story tonight. White dwarfs are everywhere. Astronomers estimate that about 97% of all stars in the Milky Way will end their lives as white dwarfs. Our Sun will become one. Sirius B, the companion star to the brightest star in our night sky, is already a white dwarf. It was one of the first to be discovered, back in the 1860s. These objects are among the most common stellar remnants in the galaxy. There are probably billions of them scattered throughout the Milky Way alone. And yet, for all their density, white dwarfs are relatively gentle objects in the grand scheme of things. They don't emit much radiation, they don't have intense magnetic fields compared to what we're about to discuss. They just sit there, slowly cooling over unimaginable spans of time. Left alone, a white dwarf is one of the most stable objects in the universe. But tonight, we're not talking about a white dwarf that's left alone. Now let's talk about the neutron star. Because if a white dwarf is strange, a neutron star is almost incomprehensible. Not every star dies as gently as the Sun will. Stars more massive than about 8 times the mass of the Sun face a much more violent end. These massive stars burn through their fuel faster and more furiously. Where the Sun will spend roughly 10 billion years fusing hydrogen, a star 20 times the Sun's mass might exhaust its hydrogen in just a few million years. And when these massive stars run out of fuel, the result isn't a gentle shedding of outer layers, it's a catastrophe. When a massive star exhausts the nuclear fuel in its core, gravity wins the tug of war instantly and decisively. The core collapses in on itself at speeds approaching a quarter of the speed of light. In less than a second, a core that was roughly the size of Earth gets crushed down to something about 12 miles across. 12 miles! You could drive across it in about 15 minutes on a highway. The outer layers of the star, no longer supported by the energy from the core, come crashing inward, slam into the newly compressed core, and bounce off in one of the most powerful explosions the universe produces. A supernova. A supernova explosion can briefly outshine an entire galaxy. Billions of stars and one single dying star rivals all of them combined. In a matter of seconds, the collapsing core radiates more energy in the form of neutrinos than the sun will produce in its entire 10 billion year lifetime. What's left behind after this explosion is the compressed core, a neutron star. And here's where things get truly extreme. A neutron star typically contains between 1.4 and about 2 times the mass of the sun, all of it packed into a sphere roughly 12 miles in diameter. Let me give you a sense of what that means. The sun is 864,000 miles across. A neutron star contains a comparable amount of mass in a sphere that's 12 miles across. That's a difference in diameter of more than 70,000 times. The compression is beyond anything we encounter in ordinary experience. The density of a neutron star is almost impossible to describe in human terms. A teaspoon of neutron star material would weigh roughly 4 billion tons. Not 4 billion pounds, 4 billion tons. That's roughly 7 times the combined weight of every human being alive on Earth today, packed into a single teaspoon. If you could somehow scoop up a teaspoonful of this material and bring it to Earth's surface, it would punch through the ground like it wasn't there, falling straight through the planet as if the rock and iron of Earth's interior were less substantial than air. The matter inside a neutron star has been compressed so thoroughly that atoms as we know them no longer exist. In ordinary matter, an atom is mostly empty space. In a white dwarf, the atoms are packed close together, but they're still recognizable as atoms. In a neutron star, the pressure is so extreme that electrons are forced into the protons, combining to form neutrons. The entire star becomes essentially a single, massive ball of neutrons, packed together as tightly as the particles in an atomic nucleus. A neutron star is, in a very real sense, a giant atomic nucleus the size of a city. What holds a neutron star up against gravity is neutron degeneracy pressure, a similar quantum mechanical effect to what supports a white dwarf, but operating between neutrons instead of electrons. The strong nuclear force also plays a role, resisting the compression of matter beyond nuclear density. Together, these forces hold the neutron star in a precarious equilibrium. If you add enough mass to push the neutron star beyond its own maximum limit, somewhere around 2 to 2.5 solar masses, depending on the equation of state of this ultra-dense matter, even neutron degeneracy pressure and the nuclear force fail. The object collapses into a black hole. Neutron stars have other extreme properties. They rotate incredibly fast. When the core of a dying star collapses from something the size of Earth to something just 12 miles across, any rotation it had gets amplified enormously, the same way a figure skater spins faster when she pulls her arms in. Some neutron stars rotate hundreds of times per second. They also have extraordinarily powerful magnetic fields, often 1 trillion times stronger than Earth's magnetic field. These magnetic fields can accelerate charged particles to nearly the speed of light, producing beams of radiation that sweep across space like cosmic lighthouses. When one of these beams happens to point toward Earth, We detect it as a pulsar, a rapid rhythmic pulse of radio waves or other radiation. The first pulsar was discovered in 1967, and for a brief time, astronomers seriously wondered if the signal might be coming from an extraterrestrial civilization. It was that regular, that precise, that unlike anything natural they had encountered before. Neutron stars are far rarer than white dwarfs because only the most massive stars produce them. But there are still estimated to be around 1 billion neutron stars in the Milky Way. Most of them are old, cold, and faint, drifting through the galaxy unseen. They're invisible to us unless they happen to be pulsars, or unless they're in binary systems where their gravity pulls matter from a companion star, heating that matter and producing X-rays we can detect. Now let's put these two objects side by side, because the comparison is what makes this story so extraordinary. A white dwarf is roughly 7,000 miles across. A neutron star is roughly 12 miles across. If you place them side by side, the neutron star would be nearly invisible, like a marble next to a hot air balloon. But now consider the mass. A typical white dwarf might contain about 6/10 the mass of the Sun. A typical neutron star might contain 1.5 times the mass of the Sun. So the neutron star, despite being nearly 600 times smaller in diameter, contains about 2.5 times more mass. In terms of volume, a white dwarf is roughly 200 million times larger than a neutron star. And yet the neutron star is significantly heavier. This means the neutron star's gravity is in a completely different league. The surface gravity of a neutron star is roughly 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star, you would be flattened to a layer of atoms thinner than a sheet of paper in a fraction of a second. Nothing with any structural integrity survives in that gravitational field. This is the fundamental setup for our story. When a white dwarf and a neutron star come together, you have an object the size of a planet encountering an object the size of a city. And the city-sized object has vastly more gravitational power. The white dwarf, for all its density, is fragile compared to the neutron star. It can be stretched, distorted, and ultimately torn apart by the neutron star's gravitational field. The smaller object can destroy the larger one, not by brute force, not by collision in the way we normally think of it, but by the sheer difference in gravitational intensity between them. This is what makes this encounter so different from, say, two planets colliding. In a planetary collision, size matters. The bigger object generally wins, but here the rules are inverted. The tiny, impossibly dense neutron star dominates. The much larger white dwarf is the vulnerable one. The question is, how do these two objects ever end up close enough for this encounter to happen? And that's where the story becomes even more fascinating. Stars don't usually exist alone. Most stars in the Milky Way are born in binary or multiple star systems. Two or more stars forming from the same collapsing cloud of gas, gravitationally bound to each other, orbiting their shared center of mass. Some estimates suggest that roughly half of all Sun-like stars have at least one companion. For more massive stars, the fraction is even higher. Binary star systems are not the exception. They're closer to the norm. In a binary system, the two stars are born at the same time from the same material, but they might have very different masses. One star might be 3 times the mass of the Sun, while the other is 8 or 9 times. They orbit each other, sometimes close together, sometimes far apart, living out their lives in a gravitational partnership that began when they were born. Here's where it gets interesting. The more massive star evolves faster. It burns through its fuel more quickly and reaches the end of its life first. If it is massive enough, above about 8 solar masses, it will eventually explode as a supernova, leaving behind a neutron star. This explosion is violent, and it kicks the system hard. The sudden loss of mass and the asymmetric nature of the explosion can give the newborn neutron star a substantial velocity kick. Sometimes, this kick is strong enough to unbind the system entirely, sending the neutron star flying off in one direction while the companion star heads in another. But sometimes the system survives. The binary stays bound. Now you have a neutron star orbiting a normal star. The companion star continues its own evolution. If it's in the right mass range, somewhere between about 1 and 8 solar masses, it will eventually swell into a red giant. As it expands, something remarkable happens. The outer envelope of the red giant can engulf the neutron star. The neutron star finds itself spiraling inside the atmosphere of its bloated companion. This is called a common envelope phase, and it's one of the most dramatic events in binary star evolution. During this phase, the neutron star spirals inward through the companion's outer layers. Friction transfers orbital energy to the envelope, causing it to be ejected into space. The neutron star and the exposed core of the companion, now on its way to becoming a white dwarf, are left in a much tighter orbit. After the common envelope is expelled, you're left with a binary system containing a neutron star and a white dwarf orbiting each other at a relatively close distance, perhaps separated by only a few solar radii. This is exactly the kind of system where gravitational wave emission becomes important. The details of common envelope evolution are still an active area of research, requiring sophisticated three-dimensional simulations that push the limits of modern supercomputers. But the broad picture is clear. Common envelope evolution is one of the primary pathways that produces tight binaries containing a white dwarf and a neutron star. And these systems are not just theoretical. Astronomers have actually observed them. Several white dwarf and neutron star binaries have been identified in the Milky Way, often detected because the neutron star is a pulsar whose precisely timed radio pulses allow astronomers to measure the orbital parameters with extraordinary precision. These observed systems confirm that such binaries exist, and that they're slowly spiraling toward each other, exactly as the theory predicts. Once you have a white dwarf and a neutron star in a tight binary orbit, something inevitable begins to happen. The system starts losing energy, not through friction, not through collisions, through something far more subtle and far more profound. It loses energy by emitting gravitational waves. Gravitational waves are ripples in space-time itself, predicted by Albert Einstein in 1916 as a consequence of general relativity. When massive objects accelerate, they create distortions in space-time that propagate outward at the speed of light. Any two orbiting objects produce gravitational waves, but for most systems the waves are so faint that the energy loss is negligible. For a compact binary, two dense objects orbiting each other at close range, the situation is very different. The gravitational waves carry away significant amounts of energy. As the system loses energy, the orbit shrinks. As the orbit shrinks, the two objects move faster and orbit more closely. As they move faster and orbit more closely, they emit even more gravitational waves. It's a runaway process. The orbit decays slowly at first, then faster and faster as the objects spiral inward. This prediction was spectacularly confirmed in 1974 when physicists Russell Hulse and Joseph Taylor discovered a binary neutron star system whose orbit was shrinking at exactly the rate predicted by general relativity for gravitational wave emission. They received the Nobel Prize in 1993. In 2015, LIGO directly detected gravitational waves for the first time, and since then has detected dozens of events from merging compact objects, including the famous neutron star merger in 2017. For a white dwarf and neutron star binary, gravitational wave emission drives the orbit to shrink over millions to billions of years, depending on how far apart the objects started. As the orbit tightens, the orbital period decreases. Two objects that might have started out orbiting each other every several hours gradually spiral inward until their orbital period drops to minutes, then to seconds. At some point, the two objects are so close that something dramatic must happen. The exact timescale depends on the initial separation and the masses of the two objects. A tighter starting orbit means less time to merger. More massive objects produce stronger gravitational waves, which also speeds up the process. For some observed white dwarf and neutron star binaries, the predicted merger timescale is within the age of the universe. These systems will eventually come together. It's not a question of if, it's a question of when. And this is the crucial point. The inspiral driven by gravitational wave emission isn't sudden. It's a slow, inexorable process that plays out over cosmic timescales. For most of the binary's life, the two objects are far enough apart that they don't significantly affect each other's structure. The white dwarf remains a white dwarf. The neutron star remains a neutron star. They're just two dense objects quietly orbiting each other while space-time ripples carry away their orbital energy one tiny wave at a time. But eventually the orbit becomes tight enough that something new enters the picture. Tidal forces. And when that happens, the white dwarf's existence begins to change in ways it cannot survive. Before we get to what those tidal forces do, there's another pathway worth mentioning. Not every white dwarf and neutron star encounter happens through this slow, gradual inspiral of a binary system. Some happen through chance. In certain parts of the galaxy, stars are packed far more densely than in our neighborhood. Globular clusters, ancient spherical collections containing hundreds of thousands or millions of stars in a region only a few dozen light years across, are among the densest stellar environments we know of. In these crowded environments, a neutron star can encounter a white dwarf through dynamical interactions thrown together by the gravitational influence of surrounding stars in ways that would never occur through normal stellar evolution. These dynamical encounters can produce white dwarf and neutron star binaries that are already in tight orbits, or in some cases, they can send the two objects on nearly direct collision courses. In a direct encounter, the white dwarf may not have the luxury of a long, gradual inspiral. It may be thrown into the neutron star's gravitational reach quickly, with less time for the gentle spiraling that characterizes the binary scenario. The physics of what happens when the two objects interact is similar in both cases, but the timescales and geometry can be very different. However, the most common and best studied pathway remains the slow inspiral of a compact binary. And it's in this scenario that we can most clearly trace what happens step by step as the white dwarf approaches the neutron star. So, picture the scene. Two stellar remnants, locked in a gravitational embrace that has lasted millions of years. A white dwarf roughly the size of Earth, packed with carbon and oxygen ash, and a neutron star, 12 miles across but containing more mass than the Sun, spinning rapidly, warping space-time around it. For most of their time together, these two objects have been orbiting peacefully. The white dwarf has been slowly cooling. The neutron star has been slowly spinning down. Their orbit has been gradually tightening as gravitational waves carry away energy. But the change from one orbit to the next is so small that it would be undetectable over human timescales. From the perspective of either object, nothing seems to be changing, but something is changing. The distance between them is shrinking, slowly, relentlessly. Each orbit brings them a tiny fraction closer. Over millions of years, that tiny fraction adds up. The orbital period drops from hours to minutes. The two objects, once separated by millions of miles, are now separated by mere hundreds of thousands. The gravitational waves grow stronger. The inspiral accelerates, and now something new begins to make itself felt. The neutron star's gravity is not uniform across the white dwarf. The side of the white dwarf facing the neutron star feels a stronger gravitational pull than the side facing away. This difference in gravitational force across the body of the white dwarf is what we call a tidal force. And as the orbit continues to tighten, as the distance between the two objects continues to shrink, these tidal forces grow stronger. At first, the white dwarf barely notices. Its own self-gravity is strong enough to hold itself together easily. But the tidal forces scale steeply with decreasing distance. Cut the distance in half, and the tidal force increases by a factor of 8. Cut it in half again, and it increases by another factor of 8. The tidal force grows rapidly, relentlessly, and there will come a point, a specific distance, where the tidal force from the neutron star exceeds the white dwarf's ability to hold itself together. When the orbit crosses that threshold, the white dwarf begins to break apart. And what follows is one of the most violent transformations in all of astrophysics. Now the question becomes, what actually happens when these two remnants get close enough to truly interact? The answer begins with something you might not expect. It's not a collision, at least not at first. It's a stretching. Because as the final stage of the inspiral plays out, as the distance drops from hundreds of thousands of miles to tens of thousands to less, something changes. One force rises above all others. Not the raw pull of gravity itself, but something more subtle and in some ways more destructive. The variation in that gravitational pull from one side of the white dwarf to the other. This gradient grows steeper every second as the orbit tightens. And once it grows strong enough, it will reshape the white dwarf in ways that are both beautiful and terrifying. That force is the tidal force. And to understand what it does to the white dwarf, we first need to understand what tidal forces actually are. You already have an intuitive sense of tidal forces. The tides on Earth are caused not simply by the moon's gravity pulling on Earth as a whole, but by the difference in the moon's gravitational pull from one side of Earth to the other. Gravity weakens with distance, following an inverse square law. Earth has a diameter of about 7,900 miles. That's not much compared to the roughly 239,000 miles between Earth and the Moon, but it's enough to create a measurable difference in gravitational pull from one side to the other. The side of Earth facing the Moon gets pulled a little more strongly toward the Moon than the center of Earth does. The side facing away from the Moon gets pulled a little less strongly. The result is that Earth gets very slightly stretched along the line connecting it to the moon. It's not stretched by much, certainly not enough for you to feel or see, but the oceans, being fluid and free to move, respond to this stretching by bulging outward on both the near side and the far side. Those bulges are the tides. That's a tidal force. It's not just gravity, it's the difference in gravity across an extended object. And this distinction matters enormously because while gravity itself simply pulls you toward a massive object, tidal forces try to stretch you. They pull harder on the near side than the far side, and this differential pull creates a stretching effect that can, under extreme enough conditions, tear an object apart. On Earth, the tidal forces from the moon are gentle. The moon is relatively small and relatively far away. The stretching is tiny. We notice it only because water is fluid and can respond to even small forces over large areas. But now imagine replacing the moon with something far more massive and far closer. Imagine replacing it with a neutron star. A neutron star packs more than a solar mass into a sphere 12 miles across. Its gravitational field is monstrously strong near its surface, and it drops off steeply with distance. This steep drop-off is exactly what makes tidal forces intense. The closer you are to a neutron star, the more dramatically the gravitational pull changes over short distances. And if you're an extended object, like a white dwarf, that rapid change in pull across your body becomes a force that tries to rip you apart. Here's the key. Tidal forces don't just depend on the mass of the object creating them, they also depend enormously on the distance. In fact, tidal forces scale with the inverse cube of the distance, not the inverse square. This means that if you halve the distance between the white dwarf and the neutron star, the tidal force doesn't just double or quadruple, it increases by a factor of 8. Halve the distance again, and it increases by another factor of 8. The tidal force grows rapidly, almost explosively, as the distance shrinks. This is why the gradual inspiral matters so much. For most of the binary's life, when the two objects are relatively far apart, the tidal forces are negligible. The white dwarf doesn't even notice the neutron star's tidal influence. But as gravitational wave emission drives the orbit tighter and tighter, there comes a point where the tidal forces begin to make themselves felt. The white dwarf starts to deform. It's no longer a perfect sphere, it begins to bulge, stretching along the line connecting it to the neutron star. At first, this deformation is subtle. The white dwarf is a solid object in the sense that its internal pressure, electron degeneracy pressure, holds it in a rigid configuration. But no object is perfectly rigid under infinite stress. The white dwarf's self-gravity wants to keep it spherical. The neutron star's tidal forces want to stretch it. As long as the self-gravity wins, the white dwarf holds its shape. But as the orbit continues to shrink, the tidal forces continue to grow. And eventually, they reach a critical threshold. This threshold has a name. Astronomers call it the Roche limit, named after the French astronomer Edouard Roche, who first calculated it in the 1840s. Roche wasn't thinking about white dwarfs and neutron stars, of course. Those objects hadn't been discovered yet. He was thinking about moons and planets, but the physics is the same. The Roche limit is the distance at which the tidal forces from a massive object become strong enough to overcome the self-gravity of a smaller object orbiting it. Inside the Roche limit, the smaller object can no longer hold itself together. The tidal forces pulling it apart exceed the gravitational forces holding it together, and the object is torn to pieces. You can see this principle at work in our own solar system. Saturn's rings are believed to exist, at least in part because they lie within the Roche limit for a body of their composition. If you tried to assemble all the particles in Saturn's rings into a single moon, you couldn't do it. Saturn's tidal forces would tear it apart again. The rings are what you get when a body exists inside the Roche limit. Debris, fragments, material spread out along the orbit rather than gathered into a coherent object. Now apply this concept to our white dwarf and neutron star binary. As the orbit shrinks and the white dwarf approaches the neutron star, it eventually crosses the Roche limit. But here's what makes this scenario more complex and more interesting than a simple moon being torn apart by a planet. The white dwarf isn't a loose pile of rubble held together only by its own gravity. It's held together by electron degeneracy pressure, an internal force that's incredibly strong. So the Roche limit for a white dwarf isn't the same as for a rocky moon or a ball of ice. The exact distance depends on the densities and internal structures of both objects, the mass ratio, and the equation of state of the white dwarf material. But there's a related concept that's even more relevant for closed binary systems, and that's the Roche lobe. The Roche lobe is a three-dimensional region around each object in a binary system. Each object's Roche lobe defines the region within which material is gravitationally bound to that object. Outside the Roche lobe, material is no longer bound. The shape of the Roche lobe isn't a simple sphere. It's a teardrop-shaped region that narrows toward the other object. The two Roche lobes in a binary system meet at a single point between the two objects called the L1 point, or inner Lagrangian point. This is the point where the gravitational pull from both objects and the centrifugal effects of the orbit exactly balance. It's a saddle point in the gravitational landscape, a narrow pass between two gravitational valleys. Here's what matters for our story. As the orbit shrinks and the two objects draw closer, the Roche lobes shrink too. Specifically, the white dwarf's Roche lobe gets smaller. Meanwhile, the white dwarf itself stays roughly the same size. At some point, the Roche lobe shrinks to the point where it's the same size as the white dwarf. When that happens, the outermost layers of the white dwarf are sitting right at the boundary of its Roche lobe. Material on the surface nearest the neutron star is barely held by the white dwarf's gravity. The slightest perturbation and it spills over. This is the moment mass transfer begins. At first, a thin stream of material flows from the white dwarf through the L1 point toward the neutron star. Picture it like water flowing over the lip of a dam. The dam is the Roche lobe boundary. The water is the white dwarf's outermost material. Once it crosses that boundary, it's no longer gravitationally bound to the white dwarf. It falls toward the neutron star, accelerating under the neutron star's immense gravity. But here's where the physics becomes critical. What happens next depends on whether this mass transfer is stable or unstable. And that distinction makes the difference between a slow, steady process and a catastrophic destruction. If mass transfer is stable, the white dwarf loses material gradually, peeling away layer by layer. It shrinks, adjusts its structure, and continues orbiting while feeding material to the neutron star at a controlled rate over thousands or millions of years. But stable mass transfer requires a specific set of conditions. In particular, it requires that as the white dwarf loses mass, it shrinks in a way that causes it to pull back within its Roche lobe, stabilizing the flow. For certain mass ratios and certain compositions, this can happen. The white dwarf loses mass, contracts, and the mass transfer proceeds at a manageable rate. However, for many white dwarf and neutron star binaries, the mass transfer is not stable. And here's why. When a white dwarf loses mass, something counterintuitive happens. White dwarfs have an unusual relationship between mass and size. In ordinary objects, removing mass makes them smaller. If you scoop material out of a ball of clay, the ball gets smaller. But white dwarfs are not ordinary objects. They're supported by electron degeneracy pressure, and this support mechanism has a peculiar property. For white dwarfs below a certain mass, removing mass actually makes the white dwarf expand. It gets larger as it loses material. This is deeply counterintuitive, but it's a direct consequence of the quantum mechanical nature of the degeneracy pressure supporting the star. As the white dwarf loses mass and its self-gravity weakens, the electrons don't need to be packed as tightly to support the remaining weight. The star puffs up. Now think about what this means for mass transfer. The white dwarf fills its Roche lobe and starts losing mass. As it loses mass, instead of shrinking away from the Roche lobe boundary, it expands, pushing even more material over the boundary. This causes it to lose mass faster, which makes it expand further, which causes it to lose even more mass. It's a runaway process, a positive feedback loop. The mass transfer accelerates out of control, feeding on itself. This is unstable mass transfer, and it leads to the complete disruption of the white dwarf. Once unstable mass transfer begins, the timescale for the white dwarf's destruction drops dramatically. What might have been a gradual process lasting thousands of years becomes a catastrophic event lasting minutes or seconds. The white dwarf doesn't just lose its outer layers, it's torn apart entirely, its material streaming toward the neutron star in massive tidal tails and spiraling debris. Consider the numbers. At the moment disruption begins, the two objects may be separated by only tens of thousands of miles. That's barely a few times the diameter of Earth. The white dwarf, roughly 7,000 miles across, is orbiting a neutron star at a distance just a few times its own width. The orbital period has dropped to less than a minute. In under a minute, the white dwarf completes a full orbit, whipping around the neutron star at velocities exceeding 1,000 miles per second. From the first moment of unstable mass transfer to the complete unraveling of the white dwarf, the process may span only a handful of these frantic orbits, perhaps a dozen, perhaps fewer. The inspiral that brought them here lasted millions of years. The final destruction plays out in less time than it takes to brew a cup of coffee. That contrast between the patient, glacial approach and the sudden, violent end is one of the most striking features of this encounter. Millions of years of quiet spiraling, followed by minutes of catastrophic destruction. The universe spent eons setting the stage, and the final act is over almost before it begins. But I want you to understand something important about how this destruction unfolds, because it's nothing like what most people imagine when they hear about two objects colliding in space. This is not a collision, not in any normal sense of the word. The white dwarf does not slam into the neutron star the way a bullet hits a wall or a car hits a barrier. There may never be a moment where the surface of the white dwarf touches the surface of the neutron star. What happens instead is far more violent and far more strange. As the white dwarf crosses the tidal threshold and begins to break apart, it doesn't shatter like glass. It's made of extremely dense fluid matter, not brittle rock. What it does is deform. It stretches along the orbital direction, elongating into an ellipsoid, then into a cigar shape. then into something that barely resembles a star at all. Material closest to the neutron star peels away first, accelerated by the enormous tidal gradient. It forms a stream, a river of ultra-dense plasma flowing toward the neutron star. Meanwhile, the rest of the white dwarf continues to orbit, continues to deform, and continues to shed material. The debris doesn't fall straight onto the neutron star because it has angular momentum from the orbital motion. Instead, it wraps around the neutron star, forming spiraling streams and eventually an accretion structure, a disk or a thick torus of white dwarf material swirling around the neutron star at tremendous speeds. Some of the material may be flung outward by the dynamics of the disruption. Tidal tails, long streams of debris, can extend far from the system in opposite directions. These tails are made of white dwarf material that gained enough energy during the disruption to escape the immediate vicinity of the neutron star, at least temporarily. Some of this material may fall back later. Some may be ejected from the system entirely. The white dwarf is sheared and stretched into spiraling filaments that wrap around the neutron star in intricate patterns. Watched from a safe distance, you would see the white dwarf transform from a compact glowing sphere into spiraling streams converging on the neutron star, all in a matter of seconds to minutes. Let me give you a sense of the energies involved, because they're staggering. As white dwarf material falls toward the neutron star, it accelerates under the neutron star's intense gravity. By the time material reaches the vicinity of the neutron star's surface, it can be traveling at a significant fraction of the speed of light. At these speeds, the kinetic energy of the infalling material is enormous. When this material decelerates, when it hits the accretion disk or the neutron star's surface or collides with other streams of debris, that kinetic energy is converted into heat. Temperatures in the accretion flow can reach billions of degrees, not millions, billions. At these temperatures, the matter is a fully ionized plasma, all the atoms completely stripped of their electrons. The photons emitted by this material are not visible light. They're X-rays and gamma rays, the most energetic forms of electromagnetic radiation. The system becomes an intense source of high-energy radiation, visible to X-ray telescopes across galactic distances. The gravitational energy released when matter falls onto a neutron star is extraordinary. Because the neutron star's surface gravity is so extreme, material falling onto it releases a far greater fraction of its rest mass energy than material falling onto, say, a white dwarf or a normal star. Roughly 10 to 20% of the rest mass energy of the accreted material can be released as radiation. For comparison, nuclear fusion in the Sun converts only about 0.7% of the mass of hydrogen into energy. Accretion onto a neutron star is more than an order of magnitude more efficient than nuclear fusion. Gram for gram, it releases more energy than any process except matter falling into a black hole. When you're disrupting an entire white dwarf, which might contain half a solar mass or more of material, the total energy released is immense. We're talking about energies comparable to a significant fraction of a supernova explosion, potentially around 10 to the power of 50 ergs or more, released over timescales ranging from seconds to hours, depending on the specifics of the disruption. But it's important to understand that not all of this energy necessarily comes out as electromagnetic radiation visible to our telescopes. A large fraction may go into the kinetic energy of outflows, into neutrino emission, or into heating material that remains gravitationally bound and radiates slowly over longer timescales. The observable signature of this event, what we would actually see with our telescopes, depends on the details of how the energy is distributed and how the debris evolves. Now, the exact character of the disruption depends on several factors, and this is where the story branches into possibilities rather than a single, inevitable outcome. First, the mass ratio matters enormously. A heavier neutron star paired with a lighter white dwarf will produce a more violent disruption than a lighter neutron star paired with a heavier white dwarf. The Roche-Loeb geometry changes with the mass ratio, and so does the orbital dynamics of the mass transfer. Second, the composition of the white dwarf matters. A carbon-oxygen white dwarf behaves differently from a helium white dwarf or an oxygen-neon-magnesium white dwarf. The composition affects the density, the equation of state, and critically, as we're about to explore, the nuclear burning that can be triggered when this material is compressed and heated. Third, the orbital parameters matter. The eccentricity of the orbit, the spin of the white dwarf, and the spin of the neutron star all affect how the disruption unfolds. A perfectly circular orbit produces a different disruption than a slightly eccentric one. A white dwarf that's been tidally locked, always showing the same face to the neutron star, disrupts differently from one that's freely rotating. Fourth, the separation at which mass transfer begins relative to the separation at which complete disruption occurs matters. In some systems, there may be a prolonged phase of stable or semi-stable mass transfer before the system reaches the point of catastrophic disruption. In others, the transition from first contact to complete destruction may be almost instantaneous. These dependencies mean that no two white dwarf and neutron star encounters are exactly alike. The physics allows for a spectrum of outcomes, from gradual whittling down of the white dwarf over thousands of years to near instantaneous disruption in a matter of seconds. The specific outcome depends on the specific properties of the system. This is a point worth emphasizing because it's tempting to think of these events as all being the same dramatic explosion. They're not. The universe is more nuanced than that. Let me also address something that's easy to overlook. The neutron star is not a passive bystander in all of this. It's not just sitting there while white dwarf material rains down on it. The neutron star has its own properties that affect the encounter. Many neutron stars spin rapidly, hundreds of times per second, dragging space-time around with them through an effect called frame dragging. This rotation affects how material accretes and can influence the dynamics of the accretion flow in important ways. Many neutron stars also have powerful magnetic fields. These fields can channel accreting material toward the magnetic poles, creating hotspots on the neutron star's surface where the infalling material strikes. If the magnetic field is strong enough, it can actually disrupt the inner accretion disk, preventing material from reaching the neutron star's surface, and instead funneling it along field lines. This affects the luminosity, the spectrum, and the time variability of the radiation produced. The neutron star's equation of state, which describes how matter behaves at the extreme densities inside the star, also matters. It determines how the neutron star responds as it gains mass from the white dwarf. Does it simply get heavier and denser? Does it eventually reach a tipping point and collapse further? We'll explore that question later, but it's important to note that the neutron star's internal structure affects the outcome of the encounter. There's another subtlety worth mentioning. In some theoretical scenarios, the disruption of the white dwarf doesn't produce a simple disk. Instead, the debris can form a thick, hot envelope surrounding the neutron star. This happens when the mass transfer rate is so high that the material can't settle into a thin disk. It's arriving faster than it can be processed. The material piles up, forming a puffy, turbulent cloud around the neutron star. This envelope can trap radiation, preventing it from escaping immediately. The radiation has to diffuse slowly through the envelope before it reaches the surface and escapes into space. This means the observable transient, the flash of light we'd see from a distance, might not look like an instantaneous explosion. It might look more like a gradual brightening and fading over days or weeks as the trapped radiation slowly leaks out. Sophisticated three-dimensional simulations tracking material flow, heating, nuclear reactions, and radiation transport have revealed a rich variety of possible outcomes. And every simulation highlights the same fundamental point. The outcome depends sensitively on the initial conditions. Change the mass of the white dwarf by 1/10 of a solar mass, and the entire character of the event can shift. And that brings us to perhaps the most remarkable aspect of this encounter. The disrupted white dwarf material doesn't just orbit the neutron star and eventually settle down. Something can happen to it that changes everything. When carbon and oxygen, the primary constituents of most white dwarfs, are compressed and heated to extreme temperatures, they can undergo nuclear fusion. Not the gentle, controlled fusion that powers main sequence stars over billions of years. Violent, runaway thermonuclear burning that can release enormous amounts of energy in seconds. Whether this nuclear burning actually happens, how intense it is, and what it produces depends on conditions that vary from system to system. But in many scenarios, the material disrupted from the white dwarf reaches temperatures and densities where nuclear ignition is not just possible, but inevitable. The white dwarf material, already one of the densest forms of matter in the universe outside of a neutron star, gets compressed even further as it spirals inward and crashes into the accretion flow. The temperatures climb from millions to hundreds of millions, and then to billions of degrees. Carbon nuclei, which have been sitting inert inside the white dwarf for billions of years since the parent star died, suddenly find themselves in conditions where they can fuse. And when carbon and oxygen start to fuse under these conditions, the energy release can be explosive. What form that explosion takes, what it looks like, and what it leaves behind, that's where our story goes next. Because the nuclear burning triggered by this disruption is what transforms this event from a gravitational catastrophe into something even more extraordinary. Something that lights up across the electromagnetic spectrum. Something that may forge new elements and scatter them into the void. Something that could, under the right conditions, push the neutron star itself over the edge. The white dwarf arrived at this encounter as a cold, quiet, ancient remnant. A stellar corpse that had been slowly cooling for billions of years. And in a matter of minutes, it was ripped apart, heated to billions of degrees, and set on nuclear fire. The energy locked in its carbon and oxygen, energy that would have remained dormant for trillions of years if left undisturbed, is now being released in a violent flash. And the neutron star, the tiny object that caused all of this, now sits at the center of a maelstrom of debris, radiation, and nuclear fury that will determine the final fate of the entire system. At this point in the story, the white dwarf no longer exists as a unified body. What was once a compact sphere, roughly the size of Earth, has been torn apart into streams and filaments of ultra-dense matter, spiraling around a neutron star. What remains is debris, And what happens to that debris is where this story becomes truly extraordinary. Let's follow the material. Every atom of carbon, every atom of oxygen that made up the white dwarf still exists, just violently reorganized into a state unlike anything it has experienced since it was forged inside a star billions of years ago. When the white dwarf breaks apart, the material closest to the neutron star is the first to go. This innermost material, already accelerated to tremendous speeds by the tidal forces, streams toward the neutron star in a narrow filament. Think of it as a river of plasma, dense beyond anything in your everyday experience, flowing at speeds that can reach tens of thousands of kilometers per second. This stream doesn't fall straight onto the neutron star. It can't, because it carries angular momentum from the orbital motion. Angular momentum is a measure of rotational motion, and it's conserved. The material was orbiting before the disruption, and it continues to orbit afterward, just in a different configuration. Because of this angular momentum, the stream of debris overshoots the neutron star. It swings around, curves past, and comes back around from the other side. As it returns, it can collide with newly arriving material still flowing from the dissolving white dwarf. This collision between streams is violent. The material crashes into itself at enormous velocities, and the kinetic energy of that collision is converted into heat. Temperatures at the collision point can reach hundreds of millions of degrees almost instantly. Over the span of minutes to hours, depending on the specifics of the disruption, the streams of debris wrap around the neutron star multiple times. Each wrap adds more material to the growing structure. The streams collide with themselves, dissipate energy, and gradually settle into a more organized configuration. What emerges from this chaos is one of two things. Depending on the rate at which the material arrives and the total amount of mass involved. If the mass transfer rate is moderate, the debris settles into a relatively thin accretion disk, a flattened rotating structure where material orbits at different speeds at different distances. Friction between these layers, driven by turbulence and magnetic fields, causes material to gradually spiral inward toward the neutron star. But if the mass transfer rate is extreme, if the white dwarf is torn apart rapidly and a large amount of material arrives in a short time, the debris doesn't have time to settle into a thin, orderly disk. Instead, it forms a thick, hot torus surrounding the neutron star. A torus is essentially a donut-shaped structure, puffed up by the enormous amount of thermal energy being generated. In the most extreme cases, the debris can form an almost spherical envelope around the neutron star, a cocoon of superheated plasma that completely surrounds the compact object. This distinction between a thin disk and a thick torus or envelope matters because it affects everything that happens afterward. It affects how quickly material reaches the neutron star's surface. It affects how radiation escapes from the system. It affects whether nuclear burning occurs and how violent that burning is. And it affects what we would actually see if we were observing this event from a distance with our telescopes. Let's talk about what happens to the material as it spirals inward through the disk or torus toward the neutron star. Because the journey from the outer edge of the debris structure to the neutron star's surface is a journey into increasingly extreme conditions. As material spirals inward, it moves into regions where the neutron star's gravity is stronger. This means the material speeds up. Conservation of energy demands that as the material falls deeper into the gravitational well, it gains kinetic energy. The orbital velocities increase. Material in the inner disk can be orbiting at velocities reaching a significant fraction of the speed of light. At the same time, friction within the disk converts some of this orbital kinetic energy into heat. The material gets hotter as it spirals inward. The temperatures climb steadily. In the outer disk, temperatures might be in the millions of degrees. As you move inward, they reach tens of millions, then hundreds of millions. Near the neutron star's surface, temperatures can exceed 1 billion degrees. The density also increases as material piles up near the neutron star. The inner regions of the disk, or torus, are compressed by the weight of the material above and around them. Densities in the inner accretion flow can reach values comparable to those found inside white dwarf material itself, and in some cases, even higher. So the material that was once part of a cold, stable white dwarf now finds itself compressed and heated to conditions that rival the cores of massive stars. And this is where something remarkable begins to happen. Something that transforms this gravitational event into a nuclear one. Carbon and oxygen, the primary elements in most white dwarfs, are nuclear fuel, though they don't burn under normal conditions. Inside a white dwarf, these nuclei have been sitting inert for billions of years, held in a dense state by electron degeneracy pressure, but completely inactive in terms of nuclear reactions. But nuclear reactions depend on temperature and density. At high enough temperatures, carbon and oxygen nuclei have enough kinetic energy to overcome the electromagnetic repulsion between their positively charged nuclei and collide with enough force to fuse. Carbon fusion, specifically the reaction where two carbon-12 nuclei combine, requires temperatures above roughly 500 million degrees. Oxygen fusion requires even higher temperatures, above about 1.5 billion degrees. These are exactly the temperatures that can be reached in the accretion flow around a neutron star during a white dwarf disruption. Now, whether nuclear burning actually ignites depends on a delicate balance between heating and cooling. The material is being heated by compression and by friction as it spirals inward. But it's also being cooled by radiation, by the emission of photons and neutrinos that carry energy away. If the heating rate exceeds the cooling rate, the temperature climbs until nuclear burning ignites. If the cooling rate is faster, the material might reach the neutron star's surface without ever igniting. The accretion rate is the critical variable. If material arrives slowly, it has time to radiate away its heat as it spirals inward. The temperatures stay moderate, and nuclear burning may not occur, or it may occur only weakly at the neutron star's surface, where conditions are most extreme. But if material arrives rapidly, faster than it can cool, the temperatures climb unchecked. The material heats up faster than it can radiate energy away, and nuclear ignition becomes inevitable. In the rapid disruption scenario, where the white dwarf is torn apart in minutes, and a large mass of debris is dumped into the accretion flow all at once, the conditions for nuclear burning are almost certainly met. The material is compressed and heated so quickly and so violently that it reaches ignition temperatures before it has any chance to cool. And when carbon and oxygen ignite under these conditions, the results can be explosive. Let me explain what happens during thermonuclear burning of carbon and oxygen, because it's different from the gentle fusion that powers ordinary stars. In a main sequence star like the Sun, hydrogen fuses into helium at a controlled, steady rate. The star is in equilibrium. If the core gets too hot, it expands slightly, which cools it down and reduces the fusion rate. If it gets too cool, gravity compresses it, heating it up and increasing the fusion rate. This self-regulating thermostat keeps the star stable for billions of years. In the disrupted white dwarf material spiraling around a neutron star, no such thermostat exists. The material is not in a self-gravitating equilibrium. It's in a rapidly evolving accretion flow, where conditions are changing on timescales of seconds. When carbon nuclei begin to fuse, the energy released heats the surrounding material, which causes more carbon to fuse, which releases more energy, which heats the material further. It's a thermonuclear runaway, a chain reaction. Once it starts, it accelerates, consuming the available fuel in a flash. The products of carbon and oxygen burning depend on the temperatures and densities involved. At moderate conditions, carbon burning produces elements like neon, sodium, and magnesium. Oxygen burning produces silicon, sulfur, phosphorus, and other intermediate mass elements. At the highest temperatures and densities, if the burning proceeds all the way to completion, the material undergoes what's called nuclear statistical equilibrium, where the nuclei rearrange themselves into the most tightly bound configuration. And the most tightly bound nucleus in nature is iron 56, or more precisely, its radioactive precursor, nickel 56. Nickel 56 is important because it's radioactive. It decays first into cobalt 56 and then into iron 56, and each decay releases energy in the form of gamma rays. In a type 1a supernova, the explosion of a white dwarf through thermonuclear detonation, this radioactive decay of nickel 56 is what powers the visible light we see for weeks and months after the explosion. The gamma rays from the decaying nickel are absorbed by the expanding debris and re-emitted as visible light, creating the characteristic light curve that astronomers use to identify these events. But I need to be very clear about something here. What happens to disrupted white dwarf material around a neutron star is not the same as a type 1a supernova. The physics has similarities, yes. Both involve thermonuclear burning of carbon and oxygen. Both can produce intermediate mass and ion group elements. But the circumstances are profoundly different. In a type 1a supernova, the entire white dwarf detonates or deflagrates as a single, self-gravitating object. The burning front propagates through the white dwarf from inside, consuming it and blowing it apart. There's no neutron star involved. The white dwarf explodes on its own, usually after being pushed to the Chandrasekhar limit by accreting material from a companion star or by merging with another white dwarf. In our scenario, the white dwarf has already been torn apart. The nuclear burning happens in the disrupted debris in streams and disk material and accreted layers on the neutron star's surface. The geometry is completely different. The confinement conditions are different. The timescales can be different. And crucially, the neutron star is sitting right there in the middle of everything. Its gravity dominating the dynamics. This means the outcome of the nuclear burning is not a simple explosion that blows everything apart. Some of the material may be ejected by the energy release, yes, but much of it remains gravitationally bound to the neutron star. The neutron star's gravity is so intense that even a powerful thermonuclear explosion in the surrounding material may not be enough to unbind all of the debris. The energy has to compete with the gravitational binding energy of the material in the neutron star's potential well, and that binding energy is enormous. So instead of a clean explosion that destroys everything, what you might get is a partial explosion. Some material is blasted outward in a fast-moving outflow. Other material falls back onto the neutron star. The outflow carries synthesized elements, newly forged nuclei of silicon and sulfur, and nickel and other products of the burning. The material that falls back adds to the neutron star's mass. The observational signature of this event, what we would actually detect with our telescopes, depends on how much material is ejected, how fast it moves, and what elements it contains. And this is where things get complicated because different simulations with different initial conditions predict quite different observational signatures. In some models, particularly those where a carbon-oxygen white dwarf is disrupted rapidly, the thermonuclear burning produces a bright transient event, an outburst of light that rises quickly and fades over days to weeks. The peak luminosity can be comparable to a faint supernova, though generally dimmer than a standard Type 1a event. The spectrum would be different too, reflecting the different composition of the ejected material and the different velocities involved. In other models, where the white dwarf is a helium white dwarf, or where the mass transfer proceeds more slowly, the nuclear burning might be less violent. Instead of a detonation where the burning front propagates supersonically through the material like a shockwave, you might get a deflagration, where the burning front moves subsonically, driven by thermal conduction rather than compression. A deflagration releases energy more slowly and produces a less dramatic explosion. And in yet other models, the nuclear burning might be confined mainly to the surface of the neutron star itself. As material accretes onto the neutron star's surface, it forms a thin, hot layer. When this layer reaches a critical temperature and density, it ignites in a thermonuclear flash. This is similar to what happens in Type 1 X-ray bursts, which are observed regularly from accreting neutron stars in binary systems. These bursts are brief, lasting seconds to minutes, and they release energy primarily as X-rays. If the accretion rate from a disrupted white dwarf is high enough, these surface flashes could be exceptionally powerful. The key insight is that the thermonuclear burning in this scenario is not all or nothing. It's a spectrum of possibilities ranging from mild surface burning to violent detonation of the entire debris structure. The outcome depends on the accretion rate, the composition, the geometry, and the dynamics of the debris flow. Different initial conditions lead to genuinely different events, with different luminosities, different spectra, different durations, and different amounts of material ejected. Now, there's another dimension to the energy release that we haven't discussed yet, and it might actually be more important than the nuclear burning in some scenarios. That's the gravitational energy. When material falls onto a neutron star, it releases gravitational potential energy. This is the energy released by falling deeper into the neutron star's gravitational well. And because the neutron star's gravity is so extreme, the amount of gravitational energy released per gram of accreted material is enormous. Let me quantify this. For material falling onto the surface of a neutron star from a large distance, the gravitational energy released is roughly 10 to 20% of the rest mass energy of the material. Rest mass energy is the energy equivalent of the material's mass. Given by Einstein's famous relationship, energy equals mass times the speed of light squared. For 1 gram of material, the rest mass energy is about 90 trillion joules. 10 to 20% of that is 9 to 18 trillion joules per gram. For comparison, The nuclear energy released by fusing 1 gram of carbon into heavier elements is roughly 100 billion joules per gram. That's impressive by earthly standards, far more energy per gram than any chemical reaction could produce. But it's only about 1% of the gravitational energy released by dropping that same gram onto a neutron star. In many scenarios, the gravitational energy released during accretion actually dominates the energy budget of the event. The nuclear burning is astrophysically important because it creates new elements. But in terms of raw energy output, gravity often wins. This has important consequences for the observable transient. Much of the light we would see from this event may be powered not by nuclear burning, but by the gravitational energy of the accretion process itself, the X-ray and gamma-ray emission from the inner accretion flow, the thermal radiation from the shock-heated debris, the luminosity of the hot envelope surrounding the neutron star. All of this is primarily gravitational energy being converted into radiation. Of course, in practice, the two energy sources are intertwined. Nuclear burning heats the material, which affects the dynamics of the accretion flow, which affects how much gravitational energy is released, and how. Separating the contributions of nuclear and gravitational energy is one of the challenges that theoretical astrophysicists face when modeling these events. Let me now talk about what happens to the material that gets ejected from the system, because this outflow has potentially profound consequences. When nuclear burning ignites in the debris, some of the material gains enough energy to escape the neutron star's gravitational well. This material is blown outward in a fast-moving wind or outflow, expanding into the surrounding space at velocities that can reach 10 to 30% of the speed of light. This outflow carries with it the products of nuclear burning, elements synthesized during the thermonuclear explosion: silicon, sulfur, calcium, titanium, chromium, iron, nickel, and potentially others. But here's where things become particularly interesting from the perspective of nucleosynthesis, the creation of new elements. In some simulations, the conditions in the outflow from a white dwarf and neutron star merger may be suitable for producing elements heavier than iron through rapid neutron capture, a process known as the R process. The R process is one of the most important mechanisms for creating heavy elements like gold, platinum, and uranium. Atomic nuclei capture neutrons in rapid succession, faster than they can decay, building up very heavy nuclei that then decay into stable heavy elements. For the R process to work, you need an environment with an extremely high density of free neutrons. Historically, core collapse supernovae were considered the primary site for the R process. More recently, the merger of two neutron stars has become the leading candidate, especially after the landmark observation of the neutron star merger in 2017, where astronomers detected signatures consistent with R process nucleosynthesis in the aftermath of the merger. But what about a white dwarf and neutron star merger? Could this also be a site for R process nucleosynthesis? The answer is maybe, but with important caveats. The material from a disrupted white dwarf is primarily carbon and oxygen, not neutrons. For R process nucleosynthesis to occur, you need a neutron-rich environment, and carbon-oxygen debris from a white dwarf is not inherently neutron-rich. However, under certain conditions, the accreted white dwarf material may interact with the neutron star's surface, or with material in the accretion disk in ways that produce neutron-rich conditions. If some of the neutron star's own material is heated and ejected, either by the energy of accretion or by the thermonuclear explosion, That material would be extremely neutron-rich and could undergo our process nucleosynthesis. The extent to which this happens and how much heavy element-enriched material is produced remains an area of active theoretical investigation. Some simulations suggest that white dwarf and neutron star mergers produce only modest amounts of our process elements, far less than a neutron star and neutron star merger. Others suggest that under specific conditions, significant heavy element production is possible. The uncertainty reflects the difficulty of modeling these events accurately. The physics involves general relativity, magnetohydrodynamics, nuclear reactions, neutrino transport, and radiation physics, all interacting simultaneously in a rapidly evolving three-dimensional flow. Even the most powerful supercomputers struggle to capture all of these effects at once. What we can say is that the outflow from a white dwarf and neutron star encounter is chemically enriched. It contains elements that were synthesized during the event, elements that the white dwarf didn't originally contain. These elements are ejected into the surrounding interstellar medium, where they mix with existing gas and dust. Over billions of years, this enriched material can be incorporated into new stars and planets. Some of the heavy elements in our own solar system, the iron in your blood, the calcium in your bones, the silicon in the rocks beneath your feet, were forged in violent events like this one. Maybe not this exact type of event, but events belonging to the same broad family of cataclysmic stellar interactions. There's another aspect of the energy release that we should discuss, one that's invisible to conventional telescopes, but potentially detectable with a different kind of instrument. Neutrinos. Neutrinos are subatomic particles with almost no mass and no electric charge that interact so weakly with matter that trillions pass through your body every second unnoticed. The sun produces enormous numbers of them through fusion, streaming in all directions and passing through Earth as if it weren't there. During the accretion of white dwarf material onto a neutron star, conditions in the inner accretion flow can become hot and dense enough to produce copious amounts of neutrinos. At temperatures above about 10 billion degrees, the primary cooling mechanism for dense matter shifts from photon emission to neutrino emission. Neutrinos carry energy away from the accretion flow far more efficiently than photons at these extreme temperatures, because neutrinos can escape directly from the densest regions, while photons get trapped and have to diffuse slowly outward. This neutrino cooling has important effects on the dynamics of the event. It removes energy from the inner accretion flow, which affects the temperature, the pressure, the nuclear burning rate, and the structure of the accretion disk or torus. In some models, neutrino cooling is the dominant energy loss mechanism in the inner regions of the accretion flow, exceeding the energy carried away by photons by orders of magnitude. From an observational standpoint, these neutrinos are extremely difficult to detect at great distances. But in principle, the neutrino emission carries information about conditions in the innermost regions of the accretion flow, regions hidden from view by the surrounding debris. If we could detect them, they would give us a direct window into the heart of the event. Let me now pull all of these threads together and paint a picture of what this event looks like from a distance, because that's ultimately what astronomers would observe if one of these encounters happened within reach of our telescopes. Imagine you're an astronomer monitoring the sky with a wide-field optical survey telescope. One night, a new point of light appears where nothing was visible before. It brightens rapidly over a few hours to a few days, reaching a peak luminosity that might be anywhere from 100th to 1/10th the brightness of a typical supernova. The color is unusual. It doesn't look like a standard supernova. The spectrum is different, showing evidence of intermediate mass elements and perhaps unusual velocity structures. Over the following days to weeks, the transient fades. The light curve, the brightness as a function of time, may show evidence of radioactive decay powering the tail of the emission. If nickel-56 was produced in the thermonuclear burning, its decay into cobalt-56 and then iron-56 releases gamma rays that heat the expanding debris and produce a slowly declining luminosity that can last for weeks. Simultaneously, X-ray telescopes might detect a bright flash from the innermost regions of the accretion flow. This X-ray emission would be powered by the gravitational energy released as material crashes onto the neutron star's surface or the inner edge of the disk. The X-ray signal might be brief, lasting only seconds or minutes, or it might persist for hours if the accretion continues at a high rate. Radio telescopes might detect emission from the interaction of the outflow with the surrounding interstellar medium. As the fast-moving ejected material plows into the thin gas between stars, it creates a shock wave that accelerates electrons to high energies. These energetic electrons spiral around magnetic field lines and emit radio waves, a process called synchrotron emission. This radio signal might appear days, weeks, or even months after the initial event, and it could persist for years. Gravitational wave detectors might pick up a signal from the final stages of the inspiral just before the disruption begins. The gravitational wave signal from a white dwarf and neutron star binary is different from the signal produced by two merging neutron stars, or two merging black holes. The frequency is typically lower because the white dwarf is larger and disrupts at a greater orbital separation. Current ground-based detectors like LIGO are most sensitive to higher frequencies, which means they're better at detecting neutron star and neutron star or black hole and black hole mergers. But future space-based detectors planned for the coming decades will be sensitive to the lower frequency gravitational waves produced by white dwarf and neutron star binaries in the years and centuries before merger. The combined picture, the optical, X-ray, radio, gravitational wave, and potentially neutrino signals taken together would tell us an enormous amount about the physics of the event. Each messenger carries different information. The gravitational waves tell us about the masses and orbital dynamics. The X-rays tell us about the innermost accretion flow. The optical light tells us about the ejected material and its composition. The radio emission tells us about the interaction with the surrounding medium. This kind of multi-messenger astronomy, combining observations across different types of signals, is one of the most exciting frontiers in modern astrophysics. The first multi-messenger observation of a neutron star merger in 2017, where gravitational waves, gamma rays, optical light, and radio waves were all detected for the same event, opened a new era in our understanding of these cosmic catastrophes. A white dwarf and neutron star merger, if observed with the same comprehensive coverage, would provide a wealth of information about a very different but equally fascinating type of event. But let me offer a word of caution. Much of what I've described so far is based on theoretical models and computer simulations. No white dwarf and neutron star merger has been definitively observed and identified as such. There are candidate events, unusual transients that don't fit neatly into existing categories. that some astronomers have suggested might be explained by this type of encounter. But none has been confirmed beyond doubt. This is partly because these events are expected to be relatively rare. Estimates vary, but the rate of white dwarf and neutron star mergers in a galaxy like the Milky Way is thought to be perhaps a few per 100,000 years to a few per million years. That's much rarer than Type 1a supernovae or core collapse supernovae. It means we might need to survey large volumes of space and monitor many galaxies to catch one in the act. It's also partly because the observational signatures are not yet well enough understood to allow definitive identification. Different simulations predict different light curves, different spectra, different timescales. Until the theoretical predictions converge, and until we have a confirmed observation that matches those predictions, the observational status of white dwarf and neutron star mergers will remain uncertain. What we do know is that the systems exist. We have observed white dwarf and neutron star binaries in the Milky Way. We know they're losing energy through gravitational wave emission and spiraling toward each other. We know that, given enough time, they will merge. The physics of the merger is well understood in broad outline, even if the details remain subjects of active research. And the nuclear fire that the merger ignites, the thermonuclear burning of carbon and oxygen in the disrupted white dwarf material, the potential synthesis of heavy elements in the outflow, the enormous release of gravitational and nuclear energy, all of this is grounded in well-established physics. The reactions that occur are the same reactions that power stars and supernovae. The gravitational dynamics follows the same equations that describe the orbits of planets and the fall of apples from trees. The novelty is not in the physics itself, but in the extreme combination of conditions, the extreme densities, the extreme temperatures, the extreme gravitational fields, and the extreme timescales. The white dwarf material has been set alight. Nuclear fire races through debris that was inert for billions of years. Energy pours out in every form the universe allows: light, X-rays, neutrinos, gravitational waves, and kinetic energy of expanding matter. And at the center of it all sits the neutron star, now wrapped in the remains of its former companion, its mass growing with every gram of material that settles onto its surface. And that growing mass raises a question that takes us to the final stage of this story. A question about limits, about thresholds, and about what happens when even a neutron star can no longer hold itself together. The neutron star now sits at the center of a storm it created. Wrapped in the shredded remains of its white dwarf companion, buried under streams and sheets and spiraling rivers of ultra-dense plasma heated to billions of degrees, it has become the gravitational anchor of a system unlike anything that existed minutes before. The white dwarf is gone as a coherent object. Its material has been torn apart, heated, compressed, and in many scenarios partially ignited in thermonuclear burning. Some of that material has been flung outward into space, but much of it remains gravitationally bound, still falling inward, still accreting onto the neutron star's surface. And this is where the final question arises. What happens to the neutron star itself? Because a neutron star, for all its extraordinary density, for all its extreme gravitational power, is not indestructible. It has a maximum mass, a ceiling above which its internal pressure can no longer support it against the crush of its own gravity. And every gram of white dwarf material that settles onto its surface pushes it closer to that ceiling. Let's talk about what that ceiling is and what happens when it's reached. A neutron star is held up by a combination of neutron degeneracy pressure and the repulsive component of the strong nuclear force. These forces resist compression, preventing the matter from collapsing further, but they can only resist so much. If you add enough mass to the neutron star, the gravitational force bearing down on its interior eventually overwhelms these internal pressures. The star can no longer hold itself up. The maximum mass a neutron star can sustain is called the TOV limit, named after the physicists who first calculated it. The exact value is one of the biggest open questions in nuclear physics and astrophysics, because the physics of matter at several times nuclear density is poorly understood. Different equations of state predict different maximum masses. Current observations constrain the TOV limit to somewhere between about 2 and 2.5 solar masses. We've observed neutron stars with masses close to 2 solar masses, so the limit must be at least that high. Some theoretical models predict it could be as high as 2.5 or even slightly higher, but somewhere in that range, there's a line. Cross it, and the neutron star collapses. What does it collapse into? A black hole. No known force can halt the collapse once neutron degeneracy pressure and the strong force are overcome. General relativity predicts the matter keeps collapsing, falling through its own event horizon. Whether a true singularity forms or whether unknown physics intervenes is one of the deepest unsolved problems, but the formation of the event horizon is essentially inevitable once the maximum mass is exceeded. Now, let's think about this in the context of our white dwarf and neutron star encounter. A typical neutron star in one of these binary systems might have a mass of about 1.4 solar masses. That's well below the TOV limit. Under normal circumstances, this neutron star would remain stable for all of eternity. It would simply cool and spin down over trillions of years, existing quietly as one of the most stable objects in the universe. But now it's accreting material from a disrupted white dwarf. A carbon-oxygen white dwarf might contain anywhere from about 4/10 to slightly above 1 solar mass of material. If a large fraction of that material falls onto the neutron star's mass increases substantially. A neutron star starting at 1.4 solar masses that accretes half a solar mass from its disrupted companion would end up at about 1.9 solar masses. That's still below the TOV limit, probably, but it's getting closer. And if the initial neutron star was heavier, say 1.8 solar masses, and the white dwarf was relatively massive, say 1 solar mass, then the accretion of even a fraction of the white dwarf's material could push the neutron star over the edge. A neutron star that accretes enough material to exceed roughly 2 to 2.5 solar masses will collapse into a black hole. The exact moment of collapse depends on the TOV limit, which we don't know precisely, but the principle is clear. Enough accretion and the neutron star dies, replaced by something even more extreme. The collapse itself would be astonishingly fast. Once the internal pressure can no longer support the mass, the neutron star caves in on itself in milliseconds. The entire object, 12 miles across, containing more mass than the Sun, collapses to a point or close to one, in a time shorter than the blink of an eye. An event horizon forms, and the neutron star is gone. In its place is a newly born black hole. What happens to the remaining debris? The material that was still in the accretion disk, still in the torus, still falling inward? Some of it gets swallowed by the black hole almost immediately. Following the neutron star's matter through the event horizon. but some of it remains in orbit, at least temporarily. The sudden formation of the black hole can also produce dramatic effects. The collapse releases a burst of gravitational waves as the space-time geometry reconfigures itself from a neutron star to a black hole. The remaining accretion disk may adjust violently to the new gravitational environment. In some theoretical models, the formation of a black hole during or shortly after a white dwarf disruption can produce a brief, intense burst of gamma rays. This would be a short gamma ray burst, lasting perhaps a fraction of a second to a few seconds. Short gamma ray bursts have been observed by space-based gamma ray telescopes for decades, and many of them are thought to originate from compact object mergers. Most confirmed short gamma ray bursts have been linked to neutron star and neutron star mergers, but it's plausible that some fraction could come from white dwarf and neutron star encounters, where the neutron star collapses into a black hole. Whether a gamma ray burst actually occurs depends on the specifics. You need certain conditions, including the formation of a brief but powerful jet of material launched along the rotational axis of the black hole or the collapsing neutron star. This jet requires strong magnetic fields and rapid rotation, conditions that may or may not be met depending on the details of the system. But collapsing into a black hole is not the only possible outcome. In fact, it may not even be the most common outcome. Let me walk through the full range of possibilities, because this is where the story becomes truly rich. Consider a scenario where the neutron star is relatively light, say 1.3 solar masses, and the white dwarf is also relatively light, say 4/10 of a solar mass. In this case, the total mass in the system is about 1.7 solar masses. Even if all of the white dwarf material falls onto the neutron star, the final mass is well below the TOV limit. The neutron star survives. It's heavier than before, hotter, spun up by the angular momentum of the accreted material, but it's still a neutron star. The accreted material settles onto its surface. The accretion disk dissipates as the last debris either falls onto the neutron star or is ejected. What remains is a solitary neutron star, more massive and spinning faster than before, possibly highly magnetized, glowing brightly in X-rays as its surface cools. Over time, thousands and millions of years, this neutron star settles down. Its rotation slows as magnetic dipole radiation carries away its rotational energy. Its surface cools. Eventually it becomes just another neutron star drifting through the galaxy. Heavier than average, perhaps with unusual surface composition or magnetic properties. But fundamentally, just a neutron star. The encounter is over. The white dwarf is gone, and the neutron star carries on alone. This is perhaps the least dramatic outcome, but it's a perfectly plausible one for systems where the combined mass stays below the collapse threshold, and where the nuclear burning doesn't produce a powerful enough explosion to significantly affect the neutron star. Now consider a different scenario. A more massive system where the nuclear burning in the disrupted material is intense. In this case, the thermonuclear detonation of the white dwarf debris releases an enormous amount of energy. The burning may propagate through a significant fraction of the debris, converting carbon and oxygen into heavier elements in a runaway chain reaction. If the energy released by this thermonuclear burning is large enough, it can unbind a substantial portion of the debris. Material that was gravitationally bound to the neutron star gets blown apart by the explosion, expanding outward at thousands of kilometers per second. This ejected material carries the freshly synthesized elements with it, scattering them into the surrounding space. The result is a transient event that looks something like a dim, fast supernova. It brightens rapidly, peaks at a luminosity that could range from a fraction of a percent to perhaps 10% of a typical Type 1a supernova, depending on the model, and then fades over days to weeks. The light at late times may be powered by the radioactive decay of nickel-56 and other unstable isotopes produced in the burning, similar to a supernova but with different amounts and therefore different brightness. As we explored earlier, this is not a Type 1a supernova, even though the same elements are burning. The geometry, the confinement conditions, and the presence of a compact remnant at the center make this a fundamentally different kind of event. What matters now is how astronomers might actually tell them apart. The light curve would likely rise and fall faster than a standard Type 1a event, and peak at a dimmer luminosity. The spectrum would reveal different velocity structures and potentially different element ratios. But the clearest difference is what's left behind. A Type 1a supernova destroys itself completely. There is no remnant. Nothing survives at the center. Our event is different. A neutron star or black hole remains, possibly detectable as an ongoing source of X-rays long after the optical transient has faded. That surviving compact object becomes a fingerprint, a way for astronomers to identify what caused the explosion and distinguish it from the far more common thermonuclear supernovae that leave nothing behind. The remnant is the giveaway. There's another comparison that needs to be addressed carefully. A kilonova. In 2017, astronomers observed the aftermath of a neutron star and neutron star merger. The event designated GW170817. The merger produced a gravitational wave signal detected by LIGO and a burst of gamma rays detected by the Fermi satellite. In the days that followed, optical and infrared telescopes detected a new source of light at the merger's location. This light was powered by the radioactive decay of heavy elements produced through R-process nucleosynthesis in the neutron-rich material ejected during the merger. This type of event is called a kilonova. A kilonova is distinctive because when two neutron stars merge, the collision ejects extraordinarily neutron-rich material that undergoes rapid neutron capture, building up very heavy radioactive nuclei whose decay powers the emission. The signature peaks in the infrared because the heavy elements produced shift the emission to longer wavelengths. A white dwarf and neutron star merger is fundamentally different. The white dwarf material is carbon and oxygen, not neutron-rich matter. The thermonuclear burning of this material produces intermediate mass elements and ion group elements, not the extremely heavy R-process elements that power a kilonova. The resulting transient, if one occurs, would have different colors, different spectra, and different timescales compared to a kilonova. There might be some overlap if neutron-rich material from the neutron star itself is ejected during the encounter. As I discussed earlier, under certain conditions, material from the neutron star's surface or the interface between the neutron star and the accretion flow could be heated and expelled. This material would be neutron-rich and could undergo R-process nucleosynthesis. But the amount of neutron-rich material ejected in a white dwarf and neutron star merger is generally expected to be much smaller than in a neutron star and neutron star merger. The kilonova component, if present at all, would be faint. So we have an event that is neither a Type 1a supernova nor a kilonova. It's something in between, something unique. Some researchers have proposed calling these events by various names, but there's no universally agreed upon terminology yet, partly because we haven't definitively observed one and confirmed its identity. There's yet another possible outcome that's worth discussing. In some scenarios, particularly where the white dwarf is a helium white dwarf rather than a carbon-oxygen white dwarf, the thermonuclear burning may trigger a detonation that doesn't just blow apart the debris, but actually produces an event with its own distinctive characteristics. A helium white dwarf has different nuclear burning properties than a carbon-oxygen white dwarf. Helium ignites at lower temperatures, and the burning can be particularly violent. In some models, the detonation of a helium shell on the surface of a neutron star or in the debris surrounding it produces a bright, fast transient that rises and falls rapidly. These events might be observable as a class of unusual fast transients that don't fit into existing supernova categories. In recent years, astronomers have discovered several types of unusual transients that don't match standard supernova templates. Some are faster than supernova, rising and fading in days rather than weeks. Some are dimmer than supernova, but brighter than ordinary novae. Some have peculiar spectral features. It's been suggested that some of these unusual events might be explained by white dwarf and neutron star mergers. One candidate that has been discussed in the literature is the rapidly evolving transient AT 2018 KZR, which showed properties that some models associate with this type of merger. However, the identification remains tentative. The honest truth is that we don't yet have a smoking gun observation. We have theoretical predictions, we have simulations, we have candidates, but we don't have a confirmed detection with multi-messenger coverage that would allow us to conclusively say this event was a white dwarf being torn apart by a neutron star. This is a frontier of astrophysics, an area where theory has outpaced observation. The events exist in nature. The binary systems that produce them have been observed. The physics governing their evolution is well established, but catching one in the act and unambiguously identifying it remains a challenge for the coming generation of telescopes and detectors. Let me now step back and look at the full landscape of possible outcomes, because this is where the story reaches its conclusion. And the conclusion is not a single definitive answer, it's a range of possibilities. At one end of the spectrum, you have a gentle encounter. A low-mass white dwarf transfers material slowly and stably onto a neutron star over thousands of years. The neutron star gains mass gradually. Some nuclear burning occurs on its surface, producing occasional X-ray flashes. But there's no catastrophic disruption, no explosion, no dramatic transient. The white dwarf is slowly consumed, and the neutron star gains mass and spins up. Eventually what's left may be a heavier millisecond pulsar, a neutron star spinning hundreds of times per second, recycled by the accretion process into rapid rotation. These recycled pulsars are actually observed in the Milky Way. Astronomers have detected several hundred of them scattered across the galaxy. Many still orbit alongside white dwarf companions, suggesting they were spun up by accreting material from a donor star that has since shrunk but not disappeared entirely. Others are found spinning alone, with no companion at all. These solitary spinners may be the aftermath of encounters where the donor was completely consumed, every last gram of its mass transferred over millions of years. If so, these isolated millisecond pulsars are direct evidence that the kind of mass transfer described tonight actually occurs in nature. They are the surviving witnesses of a white dwarf that no longer exists. They're among the most precise clocks in nature, their radio pulses arriving with metronomic regularity that rivals atomic clocks. At the other end of the spectrum, you have a catastrophic encounter. A massive white dwarf is rapidly disrupted, dumping its entire mass into the accretion flow in minutes. Violent thermonuclear burning ignites in the debris. A powerful explosion ejects a large fraction of the material at high velocities. The neutron star accretes enough of the remaining material to push it over the TOV limit, and it collapses into a black hole. The collapse produces a burst of gravitational waves and possibly a short gamma-ray burst. The ejected material expands into space, glowing as it cools, powered by radioactive decay. What remains is a newly formed black hole, perhaps still surrounded by a fading accretion disk. The only tombstone marking the graves of two stellar remnants that no longer exist. Between these extremes lies a continuum of possibilities. Partial disruptions, where only some of the white dwarf is torn apart. Moderate explosions that eject some material, but leave a surviving neutron star. Events where the nuclear burning fizzles rather than detonates, producing a dim transient rather than a bright one. Events where the neutron star gains mass, but doesn't quite reach the collapse threshold, leaving behind an unusually massive neutron star teetering near the edge of stability. And the variables that determine where on this spectrum any particular event falls are numerous. The mass of the neutron star, the mass of the white dwarf, the composition of the white dwarf, whether it's helium, carbon-oxygen, or oxygen-neon-magnesium, the orbital separation when mass transfer begins, the eccentricity of the orbit, the spin of both objects, the magnetic field strength of the neutron star, the unknown equation of state of ultra-dense matter. Each of these parameters can shift the outcome from one end of the spectrum to the other. This sensitivity to initial conditions is one of the things that makes this field both fascinating and frustrating. Fascinating because it means that nature produces a diverse range of outcomes from a single class of encounter. Frustrating because it makes prediction difficult. You can't simply say a white dwarf and neutron star merger produces this specific explosion with this specific brightness and this specific remnant. The answer is always, it depends. But this uncertainty is also what makes this an active and exciting frontier of research. Every new simulation reveals new possibilities. Every new observation of an unusual transient raises the question, could this be a white dwarf and neutron star merger? Every new gravitational wave detection from compact binary systems teaches us more about the populations of these objects, how often they merge, and what we should expect to see. Proposed detectors like the Einstein telescope in Europe and Cosmic Explorer in the United States would detect gravitational waves from compact binary mergers across a much larger volume of the universe. Space-based detectors would observe white dwarf and neutron star binaries years before they merge, tracking their inspiral in real time. On the electromagnetic side, new survey telescopes are being designed to scan the entire sky repeatedly, looking for transient events. The Vera Rubin Observatory, with its enormous camera and wide field of view, will detect millions of transients during its decade-long survey of the southern sky. Among those millions of events, there may be white dwarf and neutron star mergers hiding in plain sight, waiting to be identified by their distinctive light curves and spectra. And the theoretical work continues. Researchers are running ever more sophisticated simulations. building libraries of predicted signatures that can be compared against real data, and developing new tools to distinguish these transients from other types of events. So where does this leave us? We started this journey with 2 dead stars, a white dwarf, roughly the size of Earth, the quiet remnant of a sun-like star, and a neutron star, barely the width of a city, the ultra-dense core left behind after a massive star exploded. These are among the most extreme objects the universe produces, each one a monument to the violent processes that end a star's life. We trace the long, slow spiral that brings them together, gravitational waves draining energy from their orbit over millions of years, with a patience that's both beautiful and relentless. We watched as tidal forces stretched and distorted the white dwarf until it filled its Roche lobe, and in many scenarios lost control entirely, torn apart into streams and filaments of debris in mere minutes. We followed that debris as it wrapped around the neutron star, forming accretion disks and hot envelopes, heating to billions of degrees. We watched as nuclear fire ignited in material that had been inert for billions of years, carbon and oxygen fusing into heavier elements in a thermonuclear runaway. We examined the energy released, both gravitational and nuclear, and the outflows that carry freshly synthesized elements into the surrounding space. And we confronted the final question: what remains? The answer, as we've seen, is not singular. It depends. The remnant might be a heavier, faster spinning neutron star, or it might be a newly formed black hole. The transient might be a bright, fast explosion, or a dim, slow glow, or something in between. The ejected material might be rich in intermediate mass elements, or it might carry traces of our process heavy elements, or both. What we can say with confidence is this: these encounters happen. The binary systems that produce them are observed. The physics that governs them is well understood in broad outline. And the events they produce are unlike anything else in the universe. They are not type 1a supernovae. They are not kilonovae. They are not ordinary novae or X-ray bursts. They are their own category of cosmic event, with their own range of signatures and outcomes. And perhaps the most profound thing about these events is what they tell us about the universe itself. The universe takes dead things and makes them violent again. Stars that exhausted their fuel, that collapsed, that were supposed to be finished, are brought back into cosmic relevance by the slow, patient work of gravity. A white dwarf that could have sat quietly for trillions of years is instead torn apart and set on nuclear fire. A neutron star that might have spun down and cooled into obscurity is instead fed mass from a companion and potentially pushed to the brink of collapse. Nothing in the universe is truly finished. Even the dead stars, the remnants we think of as the endpoints of stellar evolution, can be pulled back into the story. The universe finds new uses for old materials, creating violence from stillness, complexity from destruction. The atoms forged in these encounters, the silicon and the iron and perhaps the heavier elements beyond, are scattered into the interstellar medium. Over millions of years, they mix with clouds of gas and dust. Those clouds collapse under their own gravity to form new stars and new planets. And some of those atoms end up in the molecular structures that make life possible. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of these were forged in stellar fires. Some of them may have passed through events exactly like this one, torn from a white dwarf by a neutron star's gravity, set ablaze in thermonuclear burning, and flung into space to begin the long journey toward becoming part of you. The universe is a story of cycles. Stars are born, they live, they die, and their remains are recycled into new stars and new worlds. White dwarfs and neutron stars are chapters in that story that we thought were endings. But as this encounter shows, even endings can become beginnings. The white dwarf and the neutron star spiral together in a gravitational waltz that lasts millions of years and ends in minutes. The larger object is destroyed by the smaller one. Fire erupts from ice-cold material, new elements are forged in the wreckage, and what remains, whether a heavier neutron star or a newborn black hole, carries forward the story of two dead stars into whatever comes next. That is what happens when a white dwarf collides with a neutron star, and the universe, vast and patient and endlessly creative, continues on. Thank you for joining me on this journey tonight. If this exploration changed how you think about the life and death of stars, a like or subscribe would mean a great deal. It helps me continue making these deep dives into the extraordinary physics of our universe. And the next time you look up at the night sky and see a point of light that seems peaceful and still, remember what might be happening out there beyond what your eyes can see. Dead stars, locked in spiraling embraces, falling toward encounters that will remake them in fire and gravity. The universe is never truly quiet, and even the dead are not done. Good night, and sleep well under the stars.